Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll, and today we're doing the Q&A session associated with video number 4, which was space, or at least idea number 4. The videos have been accumulating with the intro and the Q&As and everything. And so I realized when we were talking about space, when I did the video for that, I realized that I didn't organize things in the ideal way. This happens sometimes, right? Casual, informal, this was as advertised. So what I did was, I started with the idea of dimensions of space, three-dimensional space. Why is it like that? Could it have been different? Are there dynamical mechanisms that can change the number of dimensions? And then I went on to Hamiltonian mechanics, the position and momentum way of thinking about things, yet another formulation of Newtonian classical physics, and then asking the question, why is position somehow special compared to momentum? Trying to answer it by saying because interactions in the real world are local in position but not in momentum. So the second part, the Hamiltonian momentum part, is more important in some very real sense than the first part. For one thing, it's true. It's true that space is three-dimensional, but all the different ideas that I talked about why space is three-dimensional, are all entirely speculative, and they could all be completely wrong. It's important to think about them. It's important to appreciate that these ideas are out there and are contemplatable, but I wouldn't put too much credence in any of them right now. The state of the art is just not that good. And second, this difference between position and momentum is a really deep fact that people don't always appreciate, and I think needs more attention as we go forward into trying to understand the fundamental nature of reality, trying to understand the ultimate theory of everything, quantum gravity and so forth, even just understanding quantum mechanics, this relationship about why position is singled out, why we live in position space, not momentum space, is something that needs a lot more attention. But by putting it second, and by putting all this cool, fancy, speculative stuff first, people spend a lot more time and attention on the number of dimensions of space question. That's fine, but I do want to sort of flip the switch here for the Q&A video, because I want to emphasize some things about Hamiltonians and momentum, because that's really, I think it is the more important part of this particular dialogue. So let me talk a little bit about, phase space and Hamiltonians. What I want to do here really is nothing that I didn't quickly mention in the first video, but I want to emphasize it. I want to go a little bit more detail so it really sinks in. Remember that the idea of phase space was to plot something like x and p. Now, x is position, despite the fact that it begins with the letter p. P is momentum. And I'm suppressing dimensions here. So if you live in a three-dimensional space, there's 3 dimensions of x, also 3 dimensions of p. There will always be the same number of dimensions of x and p. And then you have, at every point, you have the initial conditions for some physics problem. You have the state of the system at one time. If you're Laplace's demon, the information you need to know, besides the laws of physics, is where are you in phase space? It's from that you can chug forward in time and figure out what will happen next. In the Hamiltonian way of doing things, what you do is you define a function, h, which is a function of x and p, and it's basically the total energy. So it's basically the kinetic energy plus the potential energy of the system. And the wonderful thing is, from knowing what the Hamiltonian is, just one function, you can figure out all of the laws of motion of the system. What do I mean by that? Why is that important, or why do we care? In Newtonian mechanics, we wrote F equals ma. And unlike before, where I was just trying to keep things simple and approachable, I'm drawing little vector signs over the force and the acceleration, because they both live in three-dimensional space. There's an acceleration and a force separately in each direction of space. So even though this looks like just one equation, there are 3 separate components to this equation, okay? It's a vector equation, not what we call a scalar equation, which would just have one component. And there's also the relationship P equals m times v. Momentum is mass times velocity. Again, 3 components for those equations of motion. And the nice thing about the Hamiltonian is that all these 6 equations can be derived from this single function, the Hamiltonian. That's kind of an amazing thing. That kind of compactification, if you like, from many equations into just one, that kind of unification, is what physicists like to see. That's evidence that something cool is going on. So what I wanted to do was sort of fill in some of the details. I already mentioned this before, but I want to go and be a little bit more explicit just to drive it home. So what I said last time was, what you have is, your position and your momentum. So what you want to do is chug those forward in time. You want to know what are their rates of change, what are their derivatives in time, and then you could just do calculus and figure out where the system goes. It's going to go on some trajectory in phase space. So you have x, you have p. What you want are dx dt. This is the rate of change of position with time, which most of us would ordinarily call the velocity, v. Okay, that's one thing you want. And the other thing you want is the same thing, but for momentum. So you want dp dt, the rate of change of momentum. And again, in the Newtonian way of thinking about things, we would say, well, position is mass times velocity. The rate of change of velocity is acceleration. Mass isn't changing at all. We're going to simplify our lives thinking about it that way. I once wrote a whole paper with my colleague Greg Anderson on particles whose mass changed with time, which you could get in some cosmological scenarios. You had to redo all of Newtonian mechanics because everyone always assumes that the mass is constant. But anyway, if p is ordinarily mv and the derivative of velocity is acceleration, dp dt is ma, which is just the force, right? So, in other words, the equations that we ordinarily get, what I gave you, what I just told you is true in Hamiltonian mechanics, is that dx dt is p over m. That is what you get from Hamiltonian mechanics. And indeed, looking at both sides of this equation, p over m equals v is the same as p equals mv, which we think is true. And likewise, what you get for the rate of change of momentum is the force. And indeed, F equals ma, that's also true. What I didn't quite tell you, at least I don't remember telling you, is how to actually get them from the Hamiltonian. I said it in words, but not in equations. The answer is, what you do is you take the slope of the Hamiltonian function in these two different directions, okay? In the x direction and the p direction. In calculus, we talked about taking the slope of a single curve. That's the origin of calculus, the beginning, the first most obvious thing you do, the derivative, okay? So now we're taking the derivative of a function of more than one variable. It's not just x as a function of t that we're taking the derivative of, it's h as a function of x and p. So what we do, I'm going to simplify my life here by erasing this. What we do is take what is called a partial derivative, which means we hold everything constant except for one direction we can move in, and we examine the slope in that direction. So it's like you're standing on a hillside. You can walk down the slope, or you can walk up it, or you can walk perpendicular, so the slope is more or less zero, right? Those are all different amounts of slope depending on what direction you go in. This is the mathematization of that. So the slope of the Hamiltonian in the x direction is called the partial derivative of h with respect to x, funny dh dx, and the partial derivative in the p direction is called funny dh dp. So these funny d's, which mean partial derivative, I think were invented by Laplace. No, not Laplace. Leibniz, the competitor to Newton to invent calculus. They're sort of related to the delta, which is the actual Greek letter. These funny d's that are written like this are called dels, and they're only used ever in calculus. They're not letters in anybody's alphabet. They're just special calculus symbols, and what they mean is hold everything constant, move only in one direction, hold everything except one direction constant, move in that direction, calculate the slope. This is known as the partial derivative, okay? And that's where we get these equations for the change of x and the change of p. dx dt in Hamiltonian mechanics turns out to be the partial derivative of the Hamiltonian with respect to position, with respect to momentum. So dx dt equals dh dp. That's good. What if I said, what is the rate of change of momentum? Well, you're probably going to guess, given that there's some kind of symmetry between x and p, that it's the partial derivative of h with respect to x, with respect to position. You will almost be correct. It's minus that, okay? Why is it minus that? There's a deep mathy answer that involves the symplectic structure on the manifold that we call phase space, none of which we're going to get to, or at least unless this series of videos goes on for about 130 videos. We're probably not going to get to the symplectic structure on phase space here. But what we have, you'll just trust me is true, is this equation relating momentum to the Hamiltonian and the derivatives of the Hamiltonian. So there's some kind of symmetry. It's a little bit more complicated than just replacing x with p. But the point is, from this one function h, you can just take its slope and figure out how fast position will change, how fast momentum will change. And that's all you need to move forward in time to integrate to get the solution. That's how Hamiltonian mechanics works. And what I really want to do here is dig a little bit deeper than that by doing an example. Like the spirit of these videos is not doing worked examples very much, including all the math, but sometimes that's kind of healthy thing to do. So let's actually do it. Let's do an example of a Hamiltonian and how to get the equations of motion from it. So what's the simplest example we can do? The example, what do you mean by an example? Well, we have some function of x and p, which is supposed to be the energy, kinetic energy plus the potential energy. We're going to pick the simplest function that we can pick, right? Well, what is the kinetic energy? It's 1/2 mv squared, and we said already that if you already plug in p equals mv, that is 1/2m p squared. That's the kinetic energy. Plug in p equals mv, you can check that. And then the potential energy, we said, is just going to be some function of x. But we don't want to be that abstract or that general. We want to do a specific example, so we want to actually pick some function. Let's just pick a nice symmetric looking function. How about 1/2 kx squared? Okay, so just like there's a p squared, there's an x squared. And this looks very kind of even-steven in terms of what the position is doing and what the momentum is doing in this example. In fact, this example is super famous. This is the simple harmonic oscillator. Why is it famous? Two reasons. One, because it's simple enough that you can solve all the equations exactly. The other is things that are approximately simple harmonic oscillators appear all the time in the real world. So let's imagine you have a wall here, surface, and then there's a box on the surface, and it's frictionless surface, and there's a spring connecting holding the box to the wall. So there's some position at which we'll call it x equals 0, where it's in equilibrium. The spring is neither pushing it or pulling it. K can be thought of as the strength of the spring constant. And then when you move the box in one direction or another, the spring will either push it back or pull it back to where it came from. And if you push this back and forth, this has a potential energy. V of x is in fact 1/2 kx squared. So it looks like this. It looks like a parabola as a function of x. This is the simple harmonic oscillator. That is its Hamiltonian. So when you have questions like, why is the Hamiltonian that? Why is it that function of x and p? The answer, sadly, is, well, that's the Hamiltonian that works to describe the physical behavior of this system, right? What you're really asking is, why is the world like that? And so sometimes that's the kind of question that has an answer, sometimes it's not. Right now, we're just going to say the world is like that for this particular little world with a simple harmonic oscillator in it, okay? And what we want to do is, we want to actually find how these equations, the rate of change of position is the partial of h with respect to p, the rate of change of momentum is minus the partial of h with respect to x, show how they work for this particular system, the simple harmonic oscillator. Okay, we're actually going to do the math. And so one little clue, I'll give you one clue, one math clue. We're not about solving the equations here in these videos, but we want to do it now. If you have a function y equals x squared, and you want to take the derivative, you want to take the slope, the answer is dy dx equals 2 times x. More generally, if you have x to some power, when you take its derivative, you bring that power down in front, and you lower that power by subtracting 1. So 2 minus 1 is 1, x to the 1 is just x, so the derivative of y with respect to x is 2x squared. So what do we want to do? We want to get dx dt. We want to set that equal to the partial derivative of the Hamiltonian with respect to p. So this means keep x constant. If I look at the Hamiltonian, if I keep x constant, I just fix the 1/2 kx squared. That doesn't do anything at all. All that affects anything is the p part, and I differentiate p. In fact, I differentiate p squared. So what I get is 1 over 2m times derivative of p squared, which is 2p, and guess what? That is just p over m. That looks familiar, doesn't it? Because that's what we said was the rate of change of position is p over m, but we didn't assert it here. We derived it. We derived it from this very simple form of the Hamiltonian. Likewise, if we said, what is dp dt? How quickly is the momentum changing over time? That's minus the partial derivative of h with respect to x. So that is minus, where's h over here? Here it is, minus 1/2 k, and then the derivative of x squared is 2x, so it is minus kx. What that means is exactly what our picture is showing here. If we had this box displaced a little bit, okay, so that x is some positive number. Here's now x equals 1, let's say, okay. Well, this is saying that the force that is acting on our box is minus that displacement. So the force is pulling the box back, just like it should be doing. So this is nice. I mean, I know it's math. Some of you love math, and this is all trivial and kind of boring. Some of you hate math, and this is scary and intimidating. No matter what, the point is we can use these mathematical techniques to start from an extremely simple expression right here and derive all the equations of motion in a very, very simple way. In fact, let me mention that what I said in the previous videos was there's something called the Newtonian way of doing things. It's a little bit confusing because sometimes the phrase Newtonian mechanics just means classical mechanics. Sometimes it means Newton's actual way of doing classical mechanics, F equals ma. Right now I'm using it in the latter sense. And we argued, or I said, that Newtonian mechanics is equivalent to something called the principle of least action. It's a different way of thinking about classical mechanics. And I also said that it's equivalent to this Hamiltonian way. And this is, in fact, the demonstration. What we just did with the math is a demonstration that you could derive Newtonian mechanics from the Hamiltonian. It turns out also to be true that you could skip the Newtonian step and relate the action to the Hamiltonian directly. That's another way of doing it. In fact, Hamilton, who came up with the Hamiltonian, also came up with sort of the modern version of the principle of least action, which is sometimes called Hamilton's principle, but there's details and people argue about the nomenclature, etc. Anyway, all of this is to say, this way of doing physics is very powerful. Certainly when you look at equations like this for the Hamiltonian, P and X look very, very symmetric there, right? But when you look at more complicated systems, when you look at systems that are doing something other than being a simple harmonic oscillator, you typically add more terms with x's in them. You change the dependence on x, you change the potential energy, but you don't change the 1 over 2m times p squared. The kinetic energy just is the kinetic energy, usually. There's always exceptions. So that's where the asymmetry comes in. At this level, momentum and position look exactly the same. It's only when you complicate the world and have many moving parts and many different potentials and many different forces that position and momentum start looking very, very different. Okay. That was all to make myself feel better because I wanted to give you more details about Hamiltonian mechanics. Let me actually answer some of the questions that were addressed after the video came out. So questions. One very, very, very simple one was about entangled particles. I'm not even going to write the question. I'm just going to say it in words because it takes too long. So I wrote about entangled particles. And I said, I forgot which notation I used. But if you have spin up and spin down, I said, look, they could both be spin up Or they could both be spin down, or there could be some combination of both. And a lot of people wrote in, more than one person, and said, wait a minute, I thought that when particles are entangled, their spins are always opposite. So it's one is up, one is down, or one is down, one is up. The answer is these are two different possibilities that are both real possibilities. The fact of entanglement has nothing to do with whether the spins are in the same direction or the opposite direction. It's just about the fact that they are related to each other in some way. So if your state was just this, the spins are up, both spins are up, okay? That's not entangled at all. The one spin is up, and that's completely independent of the fact that the other spin is also up, right? They're just two true facts. These are entangled because once you measure one spin, you have learned something about the other spin. Whereas this is not entangled. In fact, let me write another one. Here is one spin is up and the other spin is in a superposition of spin up and spin down. So I wrote that badly, sorry. The whole point here is this is not entangled. And this is not entangled either. You don't learn about one spin by measuring the other one. So you can have all sorts of different things. It is true that this particular state, where the spins are in opposite directions, is a very popular one. It appears a lot in a lot of real physical situations. It's often the lowest energy state for these two spins to be in. But it's not the only state. We can be in all sorts of things. That was one question. Here's another question. How can a dimension be small? So the reason why this is a question, I said dimensions can be small, but I also said that dimensions are not places to go. Like sometimes, you watch Doctor Strange and you see that there's a dark dimension with all the demons in it, and you think of a dimension as a location out there in the universe. And I try to emphasize that in physics, a dimension is just a direction in which to go. So some people caught that there seems to be some tension between that, and they said, how can a direction be small, right? I mean, a direction exists at every point. There's all the different directions you can go in. So that's a very good question because you've caught me. This is using terminology in the slapdash ways that physicists often use it. The example, I gave was something like a cylinder, very long, skinny cylinder, okay? So here you have X in this direction, and maybe Y is the direction that wraps around. At any one point on the cylinder, there are absolutely two directions you can move it, right? X and Y. There's just two. It's not like X is better than Y or anything like that. But at the same time, if you go in the Y direction, there's only so far you can go before you come back to where you left. So we use the word dimension sometimes. When we say small dimension, we don't mean there's a direction you can move in that is small. We mean there's a direction you can move in such that if you move in that direction, you can only go so far, okay? That's what the phrase a small dimension of space-time means. And the reason why that's an interesting thing is because if you imagine making that dimension smaller and smaller, right? You imagine making that circle shrinking down to smaller and smaller sizes, it becomes indistinguishable from that dimension not being there at all. So when you can only observe things at large distances, the existence of a dimension of space that is much smaller than you can observe might as well not be there at all. So there's a relationship in quantum mechanics, and this is getting us too far afield, but maybe in future videos this will become clear. Small distances correspond to high energies and large masses of particles. So big particle accelerators that can reach high energies are like microscopes that are looking at smaller and smaller distances. But there is a limit, right? Any one accelerator only goes up to a certain energy. So above the energies that particle accelerators have ever probed, if there is a dimension of space smaller than the distance corresponding to those energies, they would be invisible to us. That is, if the dimensions are at the Planck scale, which is something like 10 to the minus 15 times the smallest distance we've ever probed, we would not be able to see them at all, roughly speaking. That's what it means for a dimension or direction to be small. Okay, another good question was string theory, which we mentioned as a potential theory of gravity and other forces of nature. How many dimensions? And this is another great question. A great question in the sense that it's a perfectly valid question. You're perfectly right to be confused depending on what you've heard about string theory before. You might have heard that string theory has 26 dimensions. You might have, of space-time, dimensions of space-time in this case, not just of space. You might have heard that it has 10. You might have heard that it has 11, okay? Why do you have all these different numbers? So the answer is they're just different versions of string theory, or if you like, they are different theories that can descend from string theory in some particular situation. So the 26-dimensional number comes from what we call bosonic string theory. You might have heard that in nature, when we have fields or particles, they come in two basic varieties, bosons and fermions. Bosons can pile up on top of each other, so like Higgs bosons, photons and gravitons are bosons, W and Z bosons. Fermions take up space, so like electrons, neutrinos, quarks, etc. are fermions. It's easier for various technical reasons for field theorists to work with bosons than with fermions, so when string theorists first wrote down string theory, they didn't put fermions in. And what they found was their theory of bosonic strings only works in 26-dimensional space-time, okay? By only works, what I mean is there's some symmetries that are really, really crucial to the internal consistency of string theory, and when you quantize the theory, it turns out that those symmetries get broken unless you're in the right numbers of dimensions. So this is called the critical dimension of string theory. The number of dimensions... just dimension singular. The number of dimensions in which string theory works quantum mechanically, the symmetries are not broken. But then when you add fermions, it turns out that, the way that works, the way that is consistent with all the symmetries, etc., you add in equal amounts of fermions and bosons, and you get supersymmetry, and this is where you get superstrings. Superstrings naturally live in 10 dimensions. That's the number of dimensions of space-time in which superstrings can propagate and interact with each other consistently, coherently, not breaking any symmetries. The 11 dimensions is kind of a sneaky thing. So before there was superstring theory, there was supergravity. Supergravity is not a string theory. It is a version of general relativity, of Einstein's theory of gravity, that has been made supersymmetric. Okay, so there's no strings involved. It's field theory, but it's supersymmetric field theory. Supersymmetry, I should say, I really should tell you what that means. Supersymmetry is a symmetry between bosons and fermions. It is not a symmetry that exists in experiments, as far as we have yet been able to tell, but it might be hiding from us. It might be there, we just haven't yet observed it. It's very, very popular among many theoretical physicists. So supergravity is a version of gravity that is supersymmetric for the same kinds of reasons as we talked about. Supergravity naturally lives in 11 dimensions. And this is fun, actually. This is a fun thing to talk about here because it's a little bit of interesting history of physics in the 1980s, 1990s. There were already people working on supergravity, but supergravity doesn't have all of the nice features that string theory has. There were certain features of string theory that were hard to prove would also hold just in supergravity. So it was a plucky minority of people who worked on supergravity just out of stubbornness, and they liked it, and they weren't really looked upon very highly by the superstring people. But then it turns out that supergravity, which naturally lives in 11 dimensions, contains, even though it doesn't contain strings, two-dimensional branes. So, remember, I think I mentioned something like this. This is a brane. A brane is a two-dimensional sheet instead of a one-dimensional string. If you like, a string is a one-brane, a two-dimensional sheet is a two-brane, a three-dimensional jelly is a three-brane. There are 8-dimensional branes and the whole bit. You can imagine anything like this. It's a back construction from the word membrane, because back, hundreds of years ago, no one invented a word for an 8-dimensional object. Who knows why? So very, very naturally, supergravity contains these two-dimensional branes, but they weren't fundamental. They were just, they seemed to be features of the theory, but it was hard to know what status they had and so forth. Then in the 1990s, Joe Polchinski especially, but a bunch of other people, realized that string theory also contains a bunch of higher dimensional objects, brain-like objects of all sorts of different numbers of dimensions. So the idea that string theory was not just a theory of strings became very popular. And then the idea of supergravity with its two brains was sort of re-examined. And it was Ed Witten who actually figured out, Ed Witten, the most famous string theorist alive, he realized the following thing. Imagine you have a two-dimensional brain, but you also have one compact dimension of space. Okay, so this is, let's say you have 11 dimensions of space-time. That's 10 dimensions of space. Let's imagine you have 9 dimensions of space that are big, and then you have 1 dimension of space, this one, that is small. So this is where, this is a particular configuration in which supergravity could live, right? And then you can take a brain and you can wrap it around. So in fact, I realize that this is not the best drawing to make. Let me unwrap this, because I need to draw more than one big dimension. I drew one big dimension this way. I need to draw 2 of them. So what I want to draw is something like this. So what this is supposed to mean is, imagine you're identifying the top and bottom here. So this is actually a circle. And these are 2 big dimensions. And that's the one small dimension. So this is 3 dimensions that I've drawn here, right? 2 big, 1 small. I'm suppressing the rest of the dimensions, but imagine this is part of an 11-dimensional space-time. Okay? You get that? So if I zoomed in here, what this means is if I'm in this surface, if I walk upward and I get to the top, I suddenly, boom, appear back in the bottom. It's just like a one-dimensional torus, which we call a circle, okay? So this is 2 big dimensions and 1 circle. And imagine this is part of supergravity, so I've suppressed the other, what is it? If I have 9 dimensions of space total, no, 10 dimensions of space total, 9 of them are big, 1 of them is small. Good, that's what I drew. But now I have 2-dimensional brains living in this. So there's 2 possibilities. One is the 2-dimensional brains can sort of stretch across the big dimensions. But there's another possibility that they could just like be embedded in the small dimensions. So imagine the 2-dimensional brain did something like this. Right? So what this is saying is there's 2 dimensions, but one of them is wrapped around the small dimension of space, and the other 1 dimension is stretched into the big dimensions of space. Then to the point of view of someone who only lives in the big dimensions, some low energy observer, that 2-dimensional brain looks 1-dimensional. That is to say, it looks like a string. So what Witten realized was you could start with 11-dimensional supergravity, compactify it along 1 dimension, and the 2-dimensional brains of supergravity would become 1-dimensional strings. So he realized that there's a relationship between string theory and supergravity, and the relationship is they're both 2 different aspects of the same underlying theory, which he named M theory. That's what M theory is. It's the unknown, we still don't understand it, mother theory, magical mystery theory behind it all. And the 10-dimensional superstring theories, there are 5 of them if you want to count, are all different limits, different approximations in different circumstances of M theory. And 11-dimensional supergravity is another limit, another approximation of M theory. So that's the relationship between the 11 dimensions and the 10 dimensions. The 26 dimensions just was a good first try, okay? The 10 dimensions and 11 dimensions are real, honest, but different limits of the underlying M theory. That was probably more than you wanted to know, or more than I wanted to say, but this stuff is so cool, I just can't resist. Okay, continuing on, are there alternatives to compactification? What I mean by this is, I said there are ways to hide an extra dimension by making it small. Are there ways that we couldn't see an extra dimension even if it weren't small, even if it were big? Well, the answer is yes, otherwise I wouldn't be talking about this. And the answer comes exactly from this idea of brains. So imagine that here's some big dimensions, okay? And three big dimensions of space, and let's wrap around these three big dimensions of space, let's wrap around a brain, okay? A two-dimensional brain, just to make our lives easy. So this is the brain, and this is space. That's easy enough to do, but the important thing is people realized very early on in the theory of D-brains from Polchinski and others that there could be particles and fields stuck to the brains. Okay, that by the way, every joke relating BRANE to BRAIN has been made. There have been papers written about brain surgery and all that stuff. Okay, so forgive me for that. I'm not going to try to make them here. Anyway, you can imagine people made of particles who essentially are only living on the brains, right? Cannot get out into what is called the bulk. The bulk is the rest of the universe. So you might think that we don't have to compactify at all. What if there's a three-dimensional brain embedded in nine-dimensional space of one of the superstring theories, or 10-dimensional space of supergravity? Well, it doesn't quite work, because there is one force of nature that cannot be confined to the brain, not at least in ordinary circumstances, which is gravity. Gravity always reaches out into the bulk, because gravity is a feature of space-time itself. It's not something you can confine to a brain. So there are ways that the extra dimensions could be bigger than you think, but you have to sort of fool around a little bit. One way is that we live on a brain and the extra dimensions are bigger than, an atom, but small enough that we don't notice the gravity leaking out. Experimentally, these days, that's about 1/10 of a millimeter. So if the whole size of the extra dimension is smaller than 1/10 of a millimeter, and we are stuck on a brain inside that extra dimension, that is compatible with experiments as we know it today. The other way to do it is if the geometry of space in the bulk is so highly warped that effectively gravity doesn't get out there at all. If you change the geometry of space from being flat to being bent, then it's harder and harder, it can be harder and harder for gravity to get out. This was a theory invented by Lisa Randall and Raman Sundram. Warped compactifications. And Lisa wrote a whole book about it, Warped Passages. Again, no evidence experimentally that any of this is true. There's upper limits on how much it could be true. But the point is, you can imagine different scenarios. And in the 1990s, this was full employment for theoretical physicists to imagine different ways you could try to hide the extra dimensions. These all were wonderful, real theories that made predictions. And we went and looked for the predictions, and we haven't seen any of their predictions come true yet. It might happen tomorrow. It might happen in between when I record this and when the video appears, but right now it hasn't happened yet. So again, all this talk about extra dimensions so far is entirely hypothetical. Okay, getting a little bit more deep, if you want. It is already pretty deep, right? But there was a question about locality and holography, which I'm going to not say a lot about because we don't quite yet have the tools on our plate to think about the holographic principle, but I respect this question because it's really completely on point when it comes to locality. The point is, there are things called black holes. Here's a black hole. And a black hole, we'll get into it, but a black hole has the feature that if you're a person outside, if you fall in, you can't come back out. It's a one-way street, okay? But Stephen Hawking showed that there are particles that will be released, Hawking radiation, and what that means is that eventually the black hole will evaporate away. It will lose all of its mass and it will disappear. And there's something called the black hole information loss puzzle, relating the amount of information quantum mechanically that you could put into the black hole and get it out via the Hawking radiation. The reason why I'm mentioning this is because I'm not going to give you nearly enough details to understand it, but the insistence that the information that goes in must also eventually come out is just Laplace's demon doing the insisting, right? It's the quantum mechanical version of Laplace's demon. It's physicists being absolutely convinced that there is a conservation of information over time, that the information that exists in the universe at any one moment of time is the same at any other moment. That's what convinces them that the information must eventually come out of the black hole. But there's a lot of thought experiments associated with this and the whole thing. And what people eventually realized, Hawking radiation also implies that there's entropy that the black hole has. But the entropy turns out to be proportional to the area of the black hole's event horizon. A black hole is a sphere, or a spherical topology anyway, and it has an area for this event horizon, and you can calculate the entropy. And what that seems to imply is that the amount of information contained in a black hole is distributed on the surface area of the black hole. Now, there's no reason you should believe me when I say that. I haven't filled in the details. There's a relationship between information and entropy, and there's a relationship in the case of black holes between entropy and area. Whereas, if you just had space, if you have space and locality, if you really believed in locality, as I've been pushing here, locality might make you think, locality would make you think, that at every location in space, there's a bit of information, or at least some bits of information, some amount of information. And that information is separate from the information that is at some different location. In other words, the amount of information should scale as the volume of space. There are subtleties here because of quantum mechanics and entanglement and so forth, but the number of particles that I could put in the box should be proportional to the volume of the box. Over here, with the black hole, it seems to be proportional to the area, which is a different number. So Gerard 't Hooft, Nobel Prize-winning physicist, and Leonard Susskind, another famous physicist who appeared as a guest on the Mindscape podcast, proposed this idea of the holographic principle, that this relationship between entropy and area was real, it was physical, it was meaningful, that there was a real sense in which we can think of black holes literally as being defined by information living on their surface area. So that seems to be at odds with the idea of locality, and all I'm going to say here is, yes, it is. Yes, it is. And continues to cause great consternation. There's another version of holography called the ADS-CFT correspondence, invented by Juan Maldacena, where things are much more specific, and it's perfectly clear that locality is violated in some sense. That's a situation where you have one theory of physics, one Hamiltonian, if you want, which can be thought of as two different space-times, two different field theories living on two different universes, and those space-times have different numbers of dimensions. So there's no one-to-one map between locations in one space-time and locations in another, so locality has to be violated some way. And the upshot of this, for just answering this question, is when gravity becomes important, all these are gravity, right? ADS-CFT, black holes, the holographic principle, this only comes in when gravity becomes important. When you have non-gravitational quantum field theory, this idea of locality and all the different locations in space being separately defined makes perfect sense. The number of things that can happen scales with the volume, not with the area. But gravity changes things. And there's actually other reasons to think that once you have quantum gravity, locality can't be sacrosanct anyway. So rather than saying locality is absolutely the most important thing, how can we reconcile these weird features of it? I think that we should bite the bullet and say, look, once gravity is in the game, locality is just an approximation. Locality manifests itself, it emerges, it's an emergent phenomenon in certain situations where gravity is not that strong. And where gravity is strong, like in a black hole or in these anti-de Sitter space-time ADS universes, locality is not going to be exactly right. It's still approximately right in the same set of limiting circumstances, so that's the thing we need to understand. Not how to save locality perfectly, but why locality is even approximately true. That's why I'm emphasizing these questions about momentum and Hamiltonians, because we take locality for granted, and it's important in our brains to undo that and to remember that it didn't have to be that way, and to start asking ourselves why it is that way rather than some other way. Okay, so I think I gotta go. Even some of us, even in quarantine, we have things we need to do. So there's a few other questions that were asked that I'm just going to very, very, very quickly. And in fact, I'm going to lump them into one big question. How do extra dimensions, XDs, affect the world we observe? This is a great question because I said that while they're so small, we can't observe the dimensions directly, but there can be indirect effects. It turns out the answer is in a lot of ways. The parameters of physics. So what I mean by that is the mass of the Higgs boson, the mass of the electron, the charge of the Higgs boson and the electron, the number of dimensions of space, obviously, the number of families of particles. You know, if you know a little bit about particle physics, there's something called the electron, and it has a friend, the electron neutrino. But then it has a heavier cousin, the muon, and the muon has its own neutrino. And there's another heavier cousin, the tau, which has its own neutrino. So there's 3 generations of these particles. And in ordinary particle physics, that's just a fact. When you have extra dimensions, you can explain that fact. The number of generations of particles can be tied to the ways in which the extra dimensions are curled up. And in fact, all of these parameters, the masses and charges and so forth, depend on the size and geometry of the extra dimensions, in principle. This is the origin of the landscape of universes in the string theory multiverse. If you have lots of extra dimensions, you can curl them up in lots of different ways, and the parameters of physics all look different in those different ways. So even if the extra dimensions are invisible, they are still very important to us. And, you know, you can go on to ask, well, do they have anything to do with things like dark matter or dark energy? Maybe, probably not, but it's possible. People have absolutely explored these things. Again, this is the full employment thing. Like, even when we don't know the final answers, we can have very, very well-posed questions. When you have a new idea, like extra dimensions, it opens up the space of possibilities and makes it very, very broad. So old questions, not even that old, but questions like, what is the dark matter? When you say, well, I might have extra dimensions, could that have anything to do with dark matter? The answer should always be maybe until you investigate it very, very carefully. And that's what we do. Right now, there is no known direct relationship between extra dimensions and dark matter or even dark energy. There's clearly a potential relationship between dark energy and extra dimensions. It's too much to go into right now, but it could possibly exist because the dark energy could be one of the parameters of low energy physics, right? The energy density of the vacuum clearly can depend on the extra dimensions. But we don't have any explanation. People have tried, I've tried, other people have tried, we've written papers, but we don't have any compelling explanation for why extra dimensions would make the dark matter or dark energy have exactly the properties they do. So it's still an open question. That's why this is a fun thing to do, even though we're doing the biggest ideas and pretty basic ideas like the existence of space. It's not that hard to go from the existence of space to what are the properties of space to could these help explain some of the most pressing mysteries that we have in physics today.